Good afternoon, everyone. So today we have Shana Mutenath. She joined Iowa State a couple of years back, and before that she was a postdoctoral scholar at the University of Washington. And then before that she got her BTech and MTech degrees from Kerala University and PhD from IIT Bombay. Today she's going to talk about advanced persistent threats on cyber-physical systems. And Shana, go ahead.
Shana, you are muted, sorry.
Yes. Okay, thank you, Adarsh. Thank you for the introduction. This is actually my first year, so this is my second semester, just to point that out. So thank you all for being here. Very happy to give this talk. And today I will be talking about again, a control framework for modeling and mitigating advanced persistent threats. So in between the talk, feel free to stop me in between if you have questions. So the outline. Sorry, I'm not able to. So the outline for today's talk is, first, I will introduce what is an advanced persistent threat, why I'm motivating example. And then I will be talking about an information flow graph-based detection mechanism for detecting APTs. That's what we will call an advanced persistent threat, an APT. And then we will set up a game for detecting this APT on this information flow graph. And then we will discuss about how to solve this game. And finally, if there is time, I'll relax some of the assumptions we imposed on the work that I'm discussing today, and also briefly go through some other models that we looked at, which is a stochastic game theoretic approach for detecting APT, and also a multi-agent reinforcement learning approach for detecting APT. So without further ado, let's get started on what is an advanced persistent threat, and I'll be explaining that using this example here. So in 2013, there was a data breach at Target, and the credit card and debit card information of millions of customers was stolen. So this is an example of a real-world APT attack. And broadly speaking, this attack can be considered as consisting of 6 stages. So in the first stage, the attacker tries to send a phishing attack against Fazio Mechanical Service, which is an interface of a target network. And once that is achieved, it enters into the second stage of the attack, where it will access the target network. And once the target network is compromised, the attacker progresses to the third stage, where it gains access to vulnerable machines and install malwares on the point of service terminals. And finally, it progresses to collecting the card information of the customers from the point of service and move this data out of the target network. And lastly, the stolen data is aggregated with the card information at the adversaries server. So essentially, broadly speaking, this attack consists of multiple stages. So if we look at the properties or the different stages of attack, there are multiple stages, and these stages occur in a sequential manner. And the attacker tries to enter your system by compromising different possible entry points of the attack. And the objective of these attackers are to steal critical information from your system. So rather than causing an abrupt destruction to your system, the goal here is to remain in the system for a very long period of time and slowly, stealthily steal your critical data. So the key properties of an APT can be listed as follows. The first one, these are customized attack by intelligent adversaries. So, when they are trying to attack a target network or Facebook, it is specially tailored and customized for those networks. And also, second point is that these APTs interact with the system in a very stealthy manner. So the interactions are at a very ultra low rate that you do not necessarily see an abrupt change in the system operation. So why they are doing this is to remain undetected, so that the user doesn't identify presence of an adversary in their system. And due to these two main reasons, the conventional detection mechanisms like firewalls and antivirus softwares and intrusion detection systems, which are based on signature-based detections, fails to detect APTs. So the question that we are trying to answer is, So what trace, since these APTs are acting in the stealthy and ultra low rate manner, what trace do they leave in the system, if any, that we can leverage for detecting these attacks? And the answer to this question is information flows. The interaction of APTs with the system introduces something called as information flows. So what are information flows? So information flows are the data and control commands that happen between the different system components. So on the left, I have an example of a data flow command. So where, when you have arithmetic operation occurring on the data, it generates a data flow. And on the right, I have a control flow where there is an if statement, there is a control operation going on. So whenever the adversary is performing a data flow or a control flow, which it will have to perform the actions, then it will introduce these information flows. And these information flows will continuously get recorded in your system log. So the question then we pose is, the system log records these interactions, these information flows. So how do you construct these information flows, collect these information flows over a period of time and use that for our analysis? And that's where we utilize this graph construction called as information flow graph. And this graph construction is also referred to as provenance graph in the literature. And I'll be going into details of that now. So information flow graph is a graphical representation of the system log data, where the nodes are the system components, that is the processes, the files, and the objects that you have in your system. And there exist edges when there is a system call. If there is a read, a write, a send, or an open operation, then if a particular file was accessed, then there will be an edge between those components, right? So the whole system log can be captured as an information flow graph where the nodes are the system components and the edges are the different operations going on. So then how does the system log, how does this information flow graph grow with time, right? Because we are looking at this attacks that go on for months and maybe even more than that, right? So in this larger time horizon, how does this information flow graph grow? So to answer that, here we are looking at a simple example of an attack. So this is a camera grab attack. And this attack was done by the DARPA Transparent Computing team. So the camera grab attack can be broadly classified broadly divided into 3 key steps. So in step 1, the victim's Firefox browser is being exploited with a 0-day exploit. And in step 2, the exploited browser uses the victim's camera to spy on the user's behavior and take some pictures. And finally, in step 3, out of all the pictures that was taken, a few pictures or few images are chosen, and then that is sent to the attacker's server. So this is an example where the attacker is trying to access your camera in an unauthorized manner and take pictures using your camera, right? So we recorded the system log for this attack. And the system log, I'm just putting a screenshot of the system log here. And if we build the information flow graph for this, it results in a huge graph. And this is just for 39 minutes of recording. It resulted in a graph with more than 5,000 nodes and more than 33,000 edges. So if we record for a longer time, the graph size is going to be even more bigger, right? So setting up a game or analyzing this huge complex graph is computationally not viable. So the question we pose is, how do we reduce the workload of tracking potential malicious flows, and by how do we basically extract the relevant information from this graph? So the key idea is the ratio of malicious flows to the nominal flows is very small. So there is very less malicious flows, and because it's a stealthy attacker, and huge amount of nominal flows because lots of users using it and lots of background noise, right? So there exist pruning methods to trim these graphs, to extract the relevant information and to throw away some of the not user information, while making sure that you are not throwing away any useful information. So this method is called as pruning techniques. I'm not going into details of pruning techniques, but it's well explained in these papers cited below. Essentially, the idea is here what I have is some of the examples of some real attack data and how we and the pruned graph. So the initial graph that we get from the system log, we are calling that the cause IFG. And on the left, you see the cause IFG for a nation state attack. It is an advanced multi-stage attack. And on the right, you see the pruned graph. After applying the pruning techniques, the trimmed graph. So the initial cause IFG consists of 299 nodes and 404 edges, and we trimmed that down to a 30 node graph with 74 edges. And here I have another example for a ransomware attack, and the cause IFG consists of 173 nodes and 482 edges. And we performed the pruning again and extracted this nice graph of 18 nodes and 29 edges. So we will be setting our game on this pruned IFG rather than on the cause IFG, because this is a less complex graph to deal with. So using information flows, there exists a detection mechanism called as dynamic information flow tracking, which is used for detecting APTs. And it basically consists of three key features. The first one is tagging. So DIFT will tag all the suspicious. So I'm stressing this point, suspicious. You just don't know whether it is malicious or benign. So these are the suspicious flows. It will tag all the suspicious flows. And then it will track these tagged flows, keep on tracking it throughout the system execution time. And finally, when one of the tagged flows is used in an unauthorized manner, it will initiate some security checks. Just to demonstrate this using a toy example, let's say our pruned information flow graph looks like this, what you see on the right. And let's say the green nodes are the tagged flows. So all the information flows or all the edges that is originating from the green nodes will be tagged, which I'm showing here using a red arrow. So now if I choose the blue node here as the security checkpoint, then the DIFT will perform a security analysis here, and the suspicious flow, the flow that we are not sure whether it is malicious or benign, will be concluded either as malicious or benign. So that's what DIFT does. So DIFT is shown to be working well and with very good detection probability. But the issue is that it slows down the system 2 to 20 times. And hence, wide range implementation of DIFT is computationally prohibitive. So we asked this question, we have this very nice detection mechanism, which has really good detection rate, but then it introduces this performance overhead and slows down the system. So how can we come up with an analytical model to bypass this challenge so that to make DIFT more resource efficient and while maintaining the detection rate quite high. So that's where we'll dive into the detection game setup. But if anyone have a question at this point regarding the problem setup, feel free to ask your question.
Shana, I had one question. So you were talking about the stealthy attacks, right? So you low stealth attacks, you won't be able to identify them. So when you're pruning the information flow graph, how are you ensuring that you're not pruning some of the attacks itself? Because it could be that some of the edges which you're pruning could be the attack itself, right? How do you ensure that you're not doing that?
Yeah, so how we ensure that is, so we take a very conservative approach here. So all the potential possible entry points of the attack and all the potential targets, because we know what are the sensitive information on our system, right? So all those, since we take a very conservative approach in creating that list of potential entry points and the potential targets. So once you have that, we are doing a point-to-point pruning such a way that no edges that originate from the entry point and no edges that end at the targets will be removed. Rather, no edge which lies in a path from the entry point to the target, those will also not be removed. So this makes sure that you are trimming the graph, but not necessarily taking out any possible attack path.
Got it. Yeah, thank you.
Okay, so if there are no other questions, I will move to the detection game setup. So our approach basically consists of 4 steps, 2 pre-processing steps and 2 modeling steps. So the 2 pre-processing steps is the first to record the system log, and here we are using RAIN. This is a data recording system developed by our collaborator at Georgia Tech. So we use the RAIN framework to record the system log. So from that, we construct the coarse IFG, and then we apply the pruning techniques to abstract the pruned IFG so as to get a pruned graph, which is a compact representation of our system log data. All right. And then we formulate a dynamic game on a flow graph that we construct from this pruned IFG. And finally, we solve this game such a way that the solution to the game gives an optimal defense policy. So what I mean by optimal defense policy is, where do I place the security checkpoints, right? In that information graph, what nodes I choose as the security checkpoint, and also with what probability I need to choose them, right? So this gives a data-driven approach because we construct the IFG from the data, and also it's an analytical approach because we will be solving this game to give convergent algorithms with guarantees. So to view this game pictorially, you can look at this simple diagram here. So you have two agents, the adversary, which is the APT, and the defender, which is DIFT, and they are interacting with each other, right? So the adversary is performing action, so there is an adversarial interaction going on, and the defender is performing some security analysis, so there is defender actions also going on in the system. So if you look at the problem here, for the attacker, this is basically the goal of the attacker is to choose an attack path from the potential entry points. I'm just showing one entry point here, but it could be multiple. So the goal is to choose an attack path from the entry point and perform these transitions and finally reach the destination. By destination, I mean the target nodes, right? Because all these entry points and target, these are some nodes in this information flow graph, right? On the other hand, when I look at the defender's goal, his goal is to select these blue nodes or the security checkpoints. Where do I place the security checkpoints on this graph so that I can detect this attack? And why I cannot place security checkpoint at all the nodes? Because it will worsen the situation. We are trying to develop a resource efficient method, right? So placing a security checkpoint at every node is not what we want. So to broadly speaking, the defender's problem is to maximize the probability of detection while minimizing the resource expenditure, because there is a resource or there is a cost associated with placing the security checkpoint. And the adversary's problem, on the other hand, is to maximize the probability of evasion while reaching the target. It needs to reach the target, but also make sure that it is not getting detected. All right. So there is a strategic interaction because each of these players are trying to maximize or achieve their individual objective or goal. And this results, such a strategic interaction motivates a game theoretic framework. So a game, broadly speaking, consists of three main components. First is the set of players. So in this setting, it is the APT and the DIFT. They are the players of the game. And the action sets and policies. So what actions and policies these players choose for during this interaction. And finally, payoff of the players. How do we model this rewards and payoffs that the players get for choosing their specific actions, right? So the stochastic transition policy. So let me dive into what is the policy or the actions of the adversary here. So again, I'm using this toy example here. So the adversary's goal is to choose an attack path. So starting from the entry point, its goal is to choose an attack path so that it can reach the destination or the target. So the stochastic transition policy for the attacker can be thought of as a probability distribution over the possible set of all paths. So this big omega here is the all possible paths from entry point to destination. And the transition policy, stochastic transition policy of the attacker is a probability distribution on omega, such a way that it sums up to 1 so that it is a valid probability distribution. And by bold PA, we denote the set of all such stochastic path selection policies. So the adversary's view is when there is an information flow graph, so he is doing enough reconnaissance and he knows the network. And now how do I maximize the probability of reaching the destination, right? So the probability of reaching the destination is the sum of probability of reaching the destination through all possible paths from S to D. And here in this example, we have 4 possible paths, path 1, path 2, path 3, and path 4. So the total probability is summed over all possible paths. So the adversary is essentially trying to strategize a path selection problem here in order to evade detection and also to maximize the probability of reaching the destination. All right. And the defender, on the other hand, is trying to answer this question, how to choose the nodes to perform security analysis. So he is trying to solve for this question mark here. Do I place a security checkpoint at this node? Do I place a security checkpoint at this node? And so on. So he is trying to answer this question mark here. And the defender's stochastic policy can be considered as a probability distribution over all possible nodes. So here the big S is the set of all possible nodes. So he's putting a probability that he will choose node Si with probability PD of Si as a security checkpoint. And this value strictly lies between 0 and 1 because it's a probability. And by bold big PD, we denote the set of all such stochastic defense policies available to the defender. So the defender's view is to maximize the probability of detection, and that is the sum of the probability of detection at each node. So which is first to detect the attack at this, let's say node S3, the attacker will have to first reach S3 and then you perform security analysis there and detect it, right? So the probability of detection is probability that adversary reaches a particular node and then adversary detecting it. And that's summed over all possible nodes. So I have enumerated this here just to get a visual how this is happening. And then finally, so you can view that the defender's goal is to strategize the security checkpoint selection in order to maximize the probability of detection while minimizing the cost of detection. So now I'll go into the third component of game, which is the payoff structure. So we are considering the defender's payoff consisting of 3 key components. The first component is the resource cost. So it is a function of the defender's policy and the cost CD. So here CD denotes the cost associated with each node. So CD of SI is the node cost associated with node SI. And then there is a reward component, PT times alpha D. Here PT is the probability that defender will detect the attack. And alpha D is the reward he will get if he detects, because he is detecting the attack, so he gets a reward. And PR is a probability with which adversary will reach the destination. And in that case, defender should get a penalty because he failed to detect the attack, and hence he is getting a penalty, which is beta D, right? Likewise, the adversary's payoff consists of 2 components. The reward component, for adversary to reach the destination, he'll get a reward. And the penalty component, if he is missing and if he is getting detected, then he will get a penalty. Note that there is no resource cost for adversary here because we consider a very resourceful and adversary with infinite budget. On the other hand, defender has a resource cost and he is trying to allocate that in an efficient manner. Also note that here PT and PR, these are both functions of both PA and PD, because the probability that you will detect the attack not only depends upon the defender's decisions, but also on the adversary's decision, right? Adversary will have to reach that node for you to actually detect it. So this PT and PR probabilities here is a function of both PA and PD. So, so the payoff function for the defender can be considered as consisting of these 3 components, and attacker consists of these 2 components. And now to formally come back to our earlier figure, you have an attacker with a payoff UA and a defender with a payoff UD, and UA and UD are functions of both P and PD. That's why it's a game. It depends upon actions of both players. And it is a non-cooperative game because they have complementary interest. They have competing interest. And it is a 2-player game because we have 2 agents, APT and DIFT. It is a non-zero sum game because UA plus UD does not add up to 0. The class of games where the payoffs of the players add up to 0 are called zero-sum games. But here we have a non-zero sum game. And the difficulty is it is a non-zero sum game, and the game model does not fall into a typical conventional economic game model. So there is no standard solution approach available for solving this game, and we'll have to come up with our own methods to solve this game. So to formalize, the defender's problem is essentially now to maximize this payoff function of defender UD, which is a function of both P and PD. So he's maximizing over all possible strategies that he can choose so as to maximize UD. And the adversary's problem is to choose a policy PA so as to maximize his payoff, his or her payoff UA. And U and UD are both functions of PA and PD. And we look at this notion of solution to the game called as Nash equilibrium, which is shown by the following equation here, which basically means that no player, no agent can improve through unilaterally deviating. What I mean by that is PA star PD star is a Nash equilibrium if neither player can improve by deviating from that policy. So in the first equation here, if the attacker was deviating from the Nash equilibrium policy PA star and choosing some other policy PA, then its payoff is less than or equal to the Nash equilibrium reward, right? Likewise for the defender as well. If the defender was deviating unilaterally, single-handedly deviating from that equilibrium, he would never improve. So that makes this PA star, PD star an equilibrium, which is referred to as Nash equilibrium in literature. And so we will be looking for the solution to the game. We will be looking at this solution approach, Nash equilibrium. And I also want to point out the assumptions we have here. The assumptions are, the first one is we do not consider false positives and false negatives generated by DIFT in this work. In other words, if DIFT is performing a security analysis, we assume that it is capable of making the correct decision, whether the flow is malicious or benign. So there is no false positive and false negative generation. And the second assumption is we do not impose any cost constraint on the adversary here. So the adversary has infinite amount of resources that he can use for this path selection. So now, before diving into the solution, if there are any questions. Okay, so moving forward, for solving the games, the goal is to solve the Nash equilibrium, but we'll be first analyzing the best responses of the players. What do I mean by best responses? You will fix the strategy of one of the player and solve the optimization for the other player. To formalize this, let's consider the best response of the defender. So to find the best response of the defender, we will fix the adversary's policy to some PA and then try to find what is the best policy for the defender, right? So in other words, we'll be trying to solve this optimization problem here, but the change is that here PA is now fixed. So we fix PA and solve this optimization problem. So now it is just an optimization, but what we notice is that the payoff function that we have is not a concave function and is not a concave function. So I'm also trying to demonstrate here using a toy example, what is this best response for defender. So if you look at the figure below, the black values here denote the security cost for each node, the resource cost for each node. And the red values on the edges are the transition probabilities of the adversary. So we fix the adversarial policy, right? That's why we know what the red values are and we know the resource cost. And defender problem is trying to answer all these blue question marks here. So with what probability I should choose this node as the security checkpoint? Likewise for all the other nodes. So this is the problem that we are looking here. All right. So what we see is that UD, the payoff function of the defender, is not concave, but it has a nice structure called as submodularity. So I'll explain what is submodularity here. The mathematical definition is available here, but I'll be using this geometric figure here to explain it. Let's consider a function f, and let's say f of 1 is denoted by this circle here, and f of 3 is denoted by this circle here, right? So now if I do f of 1, 3, that is a union of the two circles, minus f of 1, that is shown by the blue shaded area, right? The difference. And if I look at the second figure here, let's say I have f of 1, f of 2, and f of 3. And now if I do f of 1, 2, 3, that is a union of all the three circles, minus f of 1, 2, union of the first and second, that is the red area. And you observe that the blue area is bigger or larger than the red dotted area. So this notion is called a submodularity, which essentially means that the incremental difference of adding an element into a bigger set is less than that of adding to a smaller set. So here I added the element 3 to a set 1, 2, and the incremental difference is red. But on the other hand, I added the same element 3 to a smaller set 1, not because f of 1 is a subset of f of 1, 2. Right? Sorry, 1 is a subset of 1, 2. So when I added the same element to a smaller set, the incremental difference is more. So this notion is called as submodularity, and we observe that this payoff function UD has this property. So just to explain that using an example here, a worked out example using a toy example. So let's consider the figure here, and let's say you have the black values, they are the resource cost. Throughout the presentation, the black values on the edges are the resource cost, the red values are the transition probabilities, and the blue values the probability with which a particular node was chosen as a security checkpoint, right? So if I compute the different components of the reward for the defender for this selection of PA and PD, what I get is the security cost is 0.7 times 2, right? 0.7 times I choose this node as a security checkpoint, and I incur a cost 2 if I do so. So the total security cost is 1.4. And the detection reward is if I detect the attack, right? And that I can detect the attack only at this node because I chose only this node as a security checkpoint. And that value is attacker first reaching there, which is 0.6 times 0.8, right? And then if the attacker reached there, I perform an analysis with 0.7, and I detect it with reward 5. So I overall get 1.68 as my detection reward. On the other hand, the misdetection penalty is if I miss the misdetection, right? So that is with 0.6 times 0.8 times 1.1 minus 0.7 corresponding to this node. I miss the attack plus the sum over all the other paths. So this is 0.6 times 0.2, which is this path here, right? This path here, and then 0.4 times 0.5, this path, and 0.4 times 0.5, this path. So the overall misdetection across all the paths, and that adds up to a value of 3.32. So the defender's payoff is negative of the security cost and plus the detection reward minus the misdetection penalty, right? So that gives me minus 3.04. Now, if I do the same thing after adding one more node into the security checkpoint. So here what I did is on this hexagon, I added one more node as a security checkpoint here, and I'm recalculating these values. So now if I look at the security cost, in addition to 1.4, I also have 0.9 times 1. So the security cost adds up to 2.3. And the detection reward, now I also have the detection probability associated with all the paths that pass through this node, right? So 0.4 times 0.5, that adds times 0.9, that is also getting added up. And 0.6 times 0.2 times 0.9, that is also getting added up. So that is what is shown here. And for all of that, I get a reward of 5. So it adds up to 3.12. And the misdetection probability, misdetection penalty value is, I'm not explaining the details here, just like all the probabilities with all the cases where you will miss the attack. For instance, 0.4 times 0.5, right? You will miss the attack if the attacker was choosing this path here, which I'm showing using my cursor, right? So for all those cases, you will get a penalty of 1.88. So in that case, the defender's payoff now will be again using calculated using minus resource cost plus the reward minus penalty, you will get minus 1.06. So overall, the gain that I'm getting for adding this additional node into the existing set is 1.98, right? I'm doing minus 1.06 minus minus of 3.04. So the overall gain or the incremental difference is 1.98. And this second case, I'm showing the same thing using a bigger set. So here I have a bigger set. So in addition to 0.7, I also have this node as my security checkpoint. And if I calculate my defender's payoff for this setting, just like we did before, I'll get a value of minus 0.34. And now I added the same node, this node marked in hexagon, the same node to this bigger set now. And I calculate the reward, the payoff of the defender for this selection of security checkpoint, I get minus 0.02. So the incremental difference is minus 0.02 minus 0.34, which is just 0.32. So to summarize this small hand calculation, what we did, what we saw is we had an initial selection, which is just this node, and we added this hexagon marked node into the set, and that gave us an additional gain of 1.98 for the defender. But on the other hand, if I added the same node to a bigger set, which has this and this, the incremental difference is just 0.32, which is less than. So this is just I'm just explaining the submodularity property via an example, but we can prove this theoretically, and we have this result which shows that the defender's payoff is DR submodular. DR stands for diminishing return. So here that is the submodularity version for continuous functions, and we show that it has this property, and by leveraging this structure, we can come up with algorithms with guarantees, optimality guarantee of the order of 1 minus 1 by E in polynomial time. So the interpretation here is the defender's problem is not non-convex, so it doesn't have that nice structure, but on the other hand, it is submodular. And hence we can leverage that property to come up with good solutions for the defender as far as the best response problem is concerned. All right. Now coming to the best response of the adversary. So the best response of the adversary is to, for that we fix the defender's policy, that is PD, and we try to solve for the best policy for the adversary, right? So again, we are solving this optimization problem here. Excuse me. We're trying to solve this optimization problem here, that is to choose a adversary strategy PA while PD is fixed. Right. So UA, PA, PD, this is also not a concave function. And also the problem size here. So this is essentially now a path selection problem. And the problem size increases exponentially with the number of nodes, because the number of paths increases exponentially with the number of nodes, right? So to explain this again using a toy example. So here the graph is known, the resource cost, that is the black values, are known. The defender's policy is fixed. So you know the blue values in each node, with what probability each node is chosen as a security checkpoint. And you are trying to solve for the red question marks. What are the probabilities for these paths, right? So what we notice is that the adversary's best response problem can be converted to a shortest path problem in graph theory. And shortest path problems are well studied in graph theory, and there exist really efficient algorithms for solving it. So how to transform this to a shortest path problem, right? So, and what are the edge weights? Because in shortest path, the goal is to find a path from a source or an entry point to a destination of minimum weight, where every edge will have a weight. So in our problem setting, what is this edge weight, and how do we transform this to a shortest path problem, right? And what we prove is that this is indeed a shortest path problem where the edge weights are given as follows. Every edge that is going into a node Si will be assigned with a weight minus log 1 minus PD of Si. So if you pick this node, let's say Si, it has a PD of Si value 0.9, right? So all the edges that is incoming to that node will have minus log 1 minus 0.9 as the edge weight. All right, so that's how we will choose the edge weights. And just to give a flavor of it, let's say PD of Si is 0. That is, that node was not chosen as a security checkpoint, right? Then minus log 1 minus PD of Si is 0. So that edge has weight 0. So, you know, adversary can, it's a free edge for the adversary. On the other hand, when PD of Si is 1, that is, that node is chosen as a security checkpoint with probability 1, then the edge weight is infinity, because that is an edge. So selecting that edge for the adversary is kind of the death situation, right? He'll be always caught. So that's how we transform the edge weights. So here I'm again pictorially demonstrating how the edge weights are. So if this is 0.3, the incoming edge here will have minus log 1 minus 0.3, right? Although you see the negative sign here, this is still a positive value because the log is for a value less than 1, right? So the edge weights are positive because shortest path problem requires that the weights are positive, right? So for this choice of values, this is how the edge weights will turn out to be, and you will get a solution to the shortest path problem. Here you will get this path that is marked boldly in red, right? So essentially what we conclude here is the adversary is solving a shortest path problem if the defender's policy was known. All right. So the best response of the adversary here is a shortest path problem, a weighted shortest path problem on the state space graph, and the edge weight is given by minus log 1 minus PD of Si to every incoming edge to node Si. right? And the interpretation here is weighted shortest path can be easily solved, and that path will give you an attack path where the adversary has maximum probability of winning. So the note I want to pose here is we solve this individual problems for the adversary and defender, that is the best responses, and that is definitely helpful, gives us insight on what is going on with respect to each of these agents, but it is not necessarily solving the game. To solve the game, we need to compute Nash equilibrium, which requires more work, right? Any question here? Okay. So now I will explain how to solve this game. So the first question for the Nash equilibrium analysis, the first question we pose is, which nodes in the information flow graph enables the detection of this adversary with high probability while minimizing the security cost, right? And from our analytical analysis, the result we get, it is indeed the minimum weighted vertex cut. So what is the vertex cut? So in a graph, a vertex cut is a set of nodes such that if you delete those nodes, it will partition the graph into two disjoint components. So if you look here in the ellipse, you have 3 nodes. If I remove those nodes, it will partition the graph into 2 components with the entry point on one component and the destination on the other component. So such a set is called as a vertex cut. And if it has minimum weight, it is called as a minimum weighted vertex cut. So here, the total weight of this collection of nodes is 1 plus 1 plus 2, which is 4. Hence, it is a minimum cut. On the other hand, this is also these 2 nodes also form a cut, but not minimum cut, because 5 plus 6 is 11, which is greater than 4, right? So that is what is a minimum cut, and we conclude that it is indeed a minimum cut or a minimum vertex cut, which is chosen as the security checkpoint. But that doesn't answer our question. We also want to know with what probabilities these cuts are chosen, right? So what probabilities? So we pose this question: with what probabilities the defender should perform security analysis at the min cut node? So to explain that, let's consider an example where suppose the defender chose the min cut nodes, that is the nodes in the ellipse, as the security checkpoints. But let's say it chose with probability PD and PD bar. Let's say it chose these 2 nodes with probability PD and the last node with probability PD bar. And let's assume PD is greater than PD bar, right? So now if the defender's policy is fixed, and you can solve for the best response of the adversary, right? So if I solve for the best response of the adversary, I get the red shown path as the best response. So the adversary is always choosing this path because PD bar is smaller, right? So the adversary has lower chance of getting detected if he chooses this path, all right? But then what you notice is that now the defender can now deviate from the strategy, because defender can now select some other value instead of PD bar, which is greater than PD, right? And still improve his payoff. So that's why it is not a Nash equilibrium. So recall that in Nash equilibrium, we defined it in such a way that no player can improve their payoff if they unilaterally deviate, right? So in this policy, in this strat policy pair, PD bar for defender and the red policy for the attacker, the defender can improve by just increasing this value. So that is why it is not a min cut. Sorry, not a Nash equilibrium, sorry. And so the key observation is performing security analysis with different probabilities at min cut nodes always leads to a non-Nash equilibrium scenario. And thus we make this condition that restrict the defender policy space such that the probability of performing security analysis is equal at all the chosen nodes. That is, for all the min cut nodes have equal probability of being chosen as a security checkpoint. All right. Likewise, for adversary, we ask this question: with what probabilities attacker should choose the attack path, right? For example, let's say an attacker chose the attack path with just chose this one path shown in red with probability 1. So it is always selecting this one path, right? So now if you solve the best response for the defender for this fixed adversarial strategy, the defender's best response is to just select this node as a security checkpoint, right? So there are 3 nodes in the min cut, but you don't have to place a security checkpoint here or here, because the adversary strategy is fixed that it is just using this path, right? So if you place here or here, you will just incur resource cost. So the best response of the defender is to select just this path, right? But then you notice that now the adversary can improve the payoff by deviating, right? So rather than choosing this path, adversary can quickly jump and choose another path. For example, let's say this one. And he can now improve he or she can improve the payoff, right? So adversary can deviate and improve payoff, and hence it is not a Nash equilibrium. So again, the observation is that selecting attack paths with different probabilities, if the adversary is choosing the attack paths with different probabilities, it always leads to a non-Nash equilibrium scenario. So the goal is to restrict the policy space for the attacker such a way that there is uniform probability across all the paths. Okay, so how am I doing on the time? Okay. So sorry.
No, go ahead. Sorry.
Okay, sure. So what we now do is, so we get these two key observations regarding the best response, right? So what we now do is we put this assumption, okay, assume adversary is choosing all the distinct paths from entry point to destination, such that it will pass through one min-cut node with uniform probability. Suppose we impose this, our key observation, let's say we impose that as an assumption, and now try to solve for the best response of the defender, right? And then we get that as the solution, defender indeed selects the min-cut nodes and also with equal probabilities. So we fix the adversary strategy to uniform, and then we get that defender is also choosing the min-cut nodes with uniform probability, and defender cannot increase the payoff by deviating, right? Likewise, we assume that the defender, say, is choosing the security checkpoints as the min-cut nodes with equal probability. And what is the best adversarial strategy now? And when we do that, we again get this result, which shows that it is indeed the uniform policy for adversary. The adversary will choose all the paths with equal probability. So the path 1 is 1 by 3, path 2 is also 1 by 3, and same for path 3 and path 4, right? So adversary just cannot increase the payoff by deviating from uniform policy. So that constitutes a Nash equilibrium now, right? Because if defender is choosing min-cut nodes with equal probability, adversary's best strategy is to choose uniform path. And if adversary was choosing uniform paths, defender's best strategy is to choose min-cut nodes with equal probability. And hence, we have this characterization for the Nash equilibrium of the game, which states that let S star be the weighted set of min-cut nodes of the corresponding information flow graph. And at Nash equilibrium, the best strategy for the defender is to perform security analysis at all the min-cut nodes with equal probability. And as far as the adversary is concerned, its goal is to select the paths with, again, uniform probability, and such that each path passes through exactly one min-cut node. So, this result is for a single stage attack. What I mean by that is, if you look at the figure here, consider the stage 1 as the information flow graph, right? This was our entry point, and this was the potential targets. We had in the previous example, we just used one, but it could be multiple. So this result is for the min-cut result is for the single stage attack, where you have one information flow graph, attacker trying to enter via a network, an entry point, and try to steal your data, which is the targets here. But typically APT attacks also consist of multiple stages, which essentially is you can stitch the different stages such a way that if it achieves or compromises or achieves the goal in stage 1, it can jump or hop on to stage 2. Where stage 2 is another IFG, which has its own target or destination. And if it is successful in stage 2, it will hop on to stage 3 and so on. So this is what we mean by a multi-attack stage, right? So here, each stage will be characterized by its own sub-goal. So this is the attack or target nodes in stage 1. The dark green is for stage 2. The even more darker green is for stage 3, and so on. So this could be done using a graph versioning technique, how to construct this stitched IFG. But in this setting, the min-cut solution we saw before does not extend to this setting. So here we are looking at a more weaker notion of equilibrium, which is called as correlated equilibrium. And here I have a simple counter example to show why the min cut doesn't work. I'm not going into details of this, but here in the first figure, I'm actually selecting the min cut nodes. This is our older graph as the min cut. And corresponding to that selection, if I look at the computation here, I get 97 PD minus 70 as the defender's payoff. And in the bottom figure, I'm not choosing a min cut, right? So min cut consists of all these three nodes, right? It also includes this. Here, this is not a min cut because it is a cut only if I add this other node as also. So this is not a min cut, but still here I'm getting a higher reward. So this is just a counter example to demonstrate why the min cut solution approach for the single stage case does not extend to a multi-stage case when I'm stitching together these graphs. All right, so here we are looking at a weaker notion, as I mentioned before, which is called as correlated equilibrium. So correlated equilibrium is a bigger set and Nash equilibrium sits inside it. So here we'll be looking at a possibly interdependent strategy for the players, and it is the equilibrium is defined in terms of expectation using this equation here. And here what we show is that for any epsilon, which is greater than 0, with probability 1 minus delta, you can achieve an epsilon correlated equilibrium with these many computations. So the computation is quadratic in the number of nodes and is linear in the number of stages. So M here is the number of stages. So if you have, it denotes the number of stages of the attack, and N here is the number of nodes in your initial IFG, the pruned IFG. Okay, so we have this result. And now I will be showing you some case studies we did using the real attack data. And for that, I'll be using a nation state attack. So here, nation state attack, it's the entry point is via a spear phishing attack, where the attacker leads the victim to a website that will be hosting ads from a malicious web server. And in stage 1 of the attack, the attacker exploits the vulnerability in the Firefox browser. And then once that is achieved, it progresses to stage 2, where it fingerprints the compromised system to detect the running processes and collect the network information. And in stage 3, a malicious program is written to the disk. And in stage 4, the attacker opens up a backdoor and exfiltrates the sensitive information, right? So this is the, we saw this graph before. This is the pruned IFG for the nation state attack, where stage 1, stage 2, these are the different stages. And those nodes are denoted by using these colors here, right? And we use this payoff function. Notice that here you will see that there is a, for alpha D, there is a J. This is now for the multi-stage. So there is a notation, there are separate values for alpha Ds and beta Ds for the different stages, because depending upon how critical different stages are, to denote that we are using J. So it's just how we extend the payoff function to the multi-stage case, right? That's all here. And we choose the cost parameters from the data. And how do we choose the tagging cost? We choose the cost using the fraction of flows passing through that node. So the idea here is, if a node is really busy, then that node should have a higher cost of being chosen as a security checkpoint. So if you look in this example here, just a small portion of the system log, this 9470 is a particular node which has more information flows passing through it when compared to 8991. So it's so the red one corresponds to a busier node. So performing security analysis at a busier node is more costly. So that's how we capture the cost of performing security analysis. And the other values, the alpha Ds and beta Ds, those parameters are handpicked now. So we chose this selection of parameters for the alpha A, alpha D, and beta Ds for the different stages. And here I have the convergence result for the correlated equilibrium for both the defender and the attacker. So the algorithm converges after some close to 200 iterations. And so now let me check on the time. So now I'll briefly go through some of the works we did after relaxing some of the assumptions we had. So recall that we had this assumption that we do not consider false positives or false negatives, right? But typically DIFT could generate false positives and false negatives. So what I mean by false positive is, suppose the security analysis is performed, right, over a benign flow. So there is a chance that 90% it will accurately classify it as a benign, but there is a false positive rate, let's say 10% of the time it will wrongly conclude it as a malicious flow. The actual flow was benign, so it should have been 100% with 100% concluded as benign, but the system will have a false positive, right? Similarly, there is a false negative rate where suppose an adversarial flow was analyzed at a process here, and with 95% of the time it is concluded malicious, so accurately concluded as malicious 95% of the time, but 5% the system is making a mistake which generates a false negative, right? So this so in the previous model we considered these values are negligible, and now we incorporate these values into our model and consider. So in this setting what happens is the game essentially now becomes a stochastic game. So there is a transition probability structure in addition to what we saw before, and which will depend upon the transition structure that will depend upon the false positive and false negative rate. So here to address this problem, we consider a stochastic game theoretic approach. We model a stochastic game and solve this game. And here the assumption here is, although there is false positive, false negative, we assume that those values are known. So if those values are known, again, the min-cut approach extends, and we perform analysis, we provide theoretical guarantee and also provide evaluations on real attack data. Here I'm showing for the data exfiltration attack. And later we further relax this assumption that what if the false positive, false negative values are unknown? And this now results in a setting where the game is of incomplete information because the system parameters are unknown. And in that case, we use a multi-agent reinforcement learning approach for tackling this problem. The details of this work is available at the paper below. It's under submission, and the codes are also available at the link below. And here we again provide guarantees for solving this game with convergence guarantees. And the idea here is to use a 2 timescale algorithm. I'm not going into details of that today. And we again implement this on real attack data. We used ransomware and showed convergence of our method and also provided analytical guarantees. And some of our ongoing work is how to incorporate cost of adversary in selecting these paths, and also how to deal with multiple attackers. We have an initial work. So this is a two-player game, right? We consider a single attacker. What if there are multiple attackers, which could be colluding and non-colluding? These are some of the questions, and also like online deployment, like how to do this in an online fashion. And other broader research questions include how to incorporate this flow tracking based detection mechanisms in electric power grid security, and also in how to develop this defense mechanism in the context of other cyber physical system security. And finally, how to leverage this information that we learned from solving the games to recover from the attack. So we detect the attacks, but if we want to recover the system, how to use this information for recovery. So here I have listed some of our references, and I want to thank all my mentors and collaborators, and also our funding agencies, DARPA and ONR, and I'm happy to take questions if you have any. Thank you.
I think we can probably have one question. And then probably it's already 1 o'clock, so probably one question and then we can stop if anyone has. So Shana, I had one question about the correlation, or the algorithm you used after the Nash equilibrium. So what kind of algorithm is it? Like, can you explain a bit more about that, if possible?
Sure. So it is a learning algorithm. Okay. And let me go to that slide here. So it is a learning algorithm, and what we consider is so the strategies could be coming from a possibly interdependent set. So previously we do not have in Nash equilibrium, the policies, the strategies of the players are independent, but here we assume that, okay, there is a probability distribution from which the players are choosing their strategy, and how do they learn it, right? So the distribution is known to the players, and they are signaling this information at every iteration of the learning algorithm so that eventually they learn their individual best strategy. So this assumption that it is possibly a joint interdependent strategy, that is why the equilibrium is not Nash, and that's why it's pushing it out of this purple circle here, and why it's a correlated equilibrium.
Got it. Thank you. So if no other questions are there, then thank you all very much. Probably like we can meet next week, and yeah, thank you.
Thank you all. Thank you all for your time.
Thanks, Shana, for the talk.
Thank you for the talk. Bye.